stroboscopic effect. On the other hand, when it spins in clockwise direction, the air is rapidly swept into the wider part of the space below the blades. Solid contact occurs, and the teetotum stops much more quickly. Clockwise, counterclockwise. The action which supports the teetotum is employed in these journal bearings. In a journal, a cylindrical shaft rotates inside a cylinder of very slightly greater diameter. The shaft assumes an eccentric position so that there is a narrowing gap into which fluid is dragged. This model journal bearing has been fitted with 3 manometers midway between its ends. The shaft is fixed with its narrowest gap at the top. The center manometer is located at the narrowest part, with the other 2 equally distant from it. Here the fluid is water and the manometers are open to the atmosphere. In the converging channel, the pressure rises above atmospheric and then falls below it an equal amount on the diverging side. Reversing the direction of rotation reverses the stresses and the pressure distribution. Very large pressure differences can result from greater eccentricities or speeds, or if the fluid is very viscous. In this case, the journal has been filled with syrup. By sealing the journal from the atmosphere, such a strong negative pressure is built up in the diverging section that cavitation bubbles appear. The bubbles get longer as the speed increases. Low Reynolds number flows are reversible when the direction of motion of the boundaries which gave rise to the flow is reversed. This may lead to some surprising situations which might almost make one believe that the fluid has a memory of its own. Here are 2 concentric cylinders. The fluid can be moved by turning the inner cylinder with this handle. The annulus between them is filled with glycerine. Into this space I introduce some dye which stays put owing to the high viscosity of the glycerine. Note its position before I start turning it. I now turn it 4 times, pushing the handle clockwise. The dye seems to mix as a drop of milk mixes when it is stirred into a cup of tea. Now I reverse the direction. And after turning exactly 4 turns, the dyed area reappears in its original position, with a little fuzziness due to molecular diffusion. To see what happens, we have a second apparatus that is filled with syrup. It has a wider gap, and we can look down on it. A little colored syrup is injected to mark the fluid. When the cylinder is turned, this fluid is stretched round the annulus. Now the inner cylinder is turned back exactly to its starting position. During the forward motion, the boundary of the fluid follows a path determined at each instant by the motion of the wall. At these very low Reynolds numbers, particles within the fluid move when the boundary moves, and they stop when it stops. During the reversed motion, the boundary of the fluid position. The motion of a rigid body is also reversible. Here is one with a gap to mark its orientation. This is set initially in the 12 o'clock position. The motion carries the body round and also makes it rotate. On reversing, the rigid body returns to its original position and orientation. If, however, a flexible body, like this bit of yarn, is inserted, the reversal of stress will alter the shape of the body so that it will not return to its original position. In the next experiments, we will look at the resistance of solid bodies at low Reynolds numbers. Here are two brass spheres in syrup. They have diameters in the ratio of 2 to 1. We release one now and the other later. When the smaller ball has one more unit to go, the larger one is released. They reach the bottom mark at the same time. The drag of a falling sphere is proportional to its diameter and to its speed. The net weight of the sphere is proportional to the cube of its diameter. The velocity is therefore proportional to d squared. They have diameters in the ratio of 2 to 1, so that the larger one falls in syrup 4 times as fast as the smaller. At low Reynolds numbers, the disturbance produced by a moving ball extends many diameters, so that beads far from the ball are moved by its passing. Thus, the presence of a nearby wall can be important. Here are two identical balls, one near a wall and one far from it. The ball near the wall falls more slowly. Incidentally, it remains at a constant distance from the wall, a consequence of reversibility. This retarding effect also slows the fall of a particle surrounded by many similar ones, so that a cloud of them falls more slowly than a single one. When a cloud of assorted particles falls in a fluid, it develops a sharply defined top.